Now next theorem is, let y be a fixed vector in a Hilbert space H and fy be a scalar valued function which is defined by fy of x is equal to inner product of xy for every x belongs to H, then fy belongs to H star. Further show that norm of y, which is called norm of fy. So this is a conjugate space. So first, what is a conjugate space? Conjugate spaces. So conjugate spaces, if H is a Hilbert space, if H is Hilbert space and all function bounded functional from H to C. H is a Hilbert space, C is a field, it's a complex number. So all the bounded linear functional, the linear transformation from H to C is called a conjugate space. So it is denoted by H star. So it is denoted by H star. Now, so understand the sum result. Let y be some vector belongs to H, it be a fixed vector. So it is a fixed vector. If it is a fixed vector, so we define a mapping X, which is a inner product X comma Y for every X belongs to H. Now to prove that it is a linear transformations. So what is linear transformation? So I take x1, x2 belongs to H and alpha, beta are scalars. Alpha, beta are scalars. Then it means fy of alpha x1 plus beta x2, by definition this can be written as inner product alpha x1 plus beta x2 comma y. So by using the property of inner product, this can be written as alpha x1 comma y plus beta x2 comma y. This value, now substitute its value. So this value will become alpha fy of x1 plus beta fy of x2. So it means it is a linear transformation. So this mapping is a linear transformations. Now next, it is a bounded. To prove the bounded, now norm of fy of x, so by inner product, so this can be written as inner product of x comma y. So here I will take absolute value in this norm. So absolute value by Cauchy-Scavarge inequality. So this is a norm of x into norm of y. So if I take this as a norm of x into this values, and if I take this as a constant, so it implies this function f of y, which is a bounded linear transformation. Bounded linear transformation. Linear transformations, right? Because what is the bounded linear transformation? Norm of fx, it should be norm of f into norm of x. So it means this is treated as constant, so it is a bounded linear transformation. In addition to that, our next step is norm of fy and norm of y, they are equal. So just substitute its value. What is its value? It is a supremum of fy of x, this absolute value, such that norm of x less than equal to 1. As we know that this value is less than equal to norm of x into norm of y, and again norm of x is less than equal to 1, so this value is less than equal to norm of y. So I take it as equation number 1. Now to prove this result, my claim is only to show that norm of fy is always greater than equal to norm of y, this values. Now if y is, if function is, if y is 0, suppose if y is 0, then this functional value is 0, this y is 0, so this condition is satisfied. Now we will prove if y is not equal to 0. If y is not equal to 0, so what is fy? So by definition, so this is equal to supremum of this fy of x such that norm of x less than equal to 1, these values. Now this is a supremum of all vectors, image of all vector whose norm is less than equal to 1. If I take a vector this, now what its norm? Its norm is 1. So it means supremum is always greater than equal to fy of single element y over norm of y, these values. Now using the definition, this value is equal to y over norm of y comma y. So it treated as a alpha, so this is norm of y, inner product y comma y. So this will become norm of y raised to power 2 norm of y. So this is a norm of y. So this is taken as equation number 2. Combine 1 and 2, what we get? We get norm of fy which is equal to norm of y. It proves our result. Now in this theorem, I start from a vector y belongs to h, then find a functional, then I find a functional. Now converse of this theorem is called a rise representation theorem that we will discuss in the next lecture. What is that theorem? In that theorem, if fy, if we have some functional f belongs to h star, then there exists some unique vector which satisfy the same condition, right? So that is called a rise representation